right, some of this I'm gonna go through quickly enough so that you are aware of it and can delve into the book or the slides or some other avenues to fill into it further. We've gone through all of this. We've gone through 4 addition reactions. Just know the slides are here. I did most of this on the board. Last week we talked about symmetrical and unsymmetrical reactants, hydrogen being symmetrical, halogens being symmetrical, water being unsymmetrical, and here's your isopropyl alcohol right here, and your propyl alcohol, or 1-propanol, 2-propanol, and Markovnikov's rule. Did we go through that? No, we didn't go. Okay. You got to know Markovnikov's rule. Okay, got to know Markovnikov's rule. And this is, all right, I thought we had gone a little bit further than this. This is important, Markovnikov's rule. Markovnikov's rule comes into play with the unsymmetrical reactants. That's water and a hydrohalogen. So water, and if I wrote it this way, or a hydrohalogen like this, they're unsymmetrical. What do we have here? For water, we're going to be focusing on this bond. We're going to add water across a double bond. Part of the water molecule is going to go on one of the carbons, part of it. The other part of it is going to go on the other carbon, but you can see the 2 parts are different. That's what we mean by unsymmetrical. The 2 sides of the molecule are not identical. Likewise with hydrogen and bromine. Half of the molecule is hydrogen, the other half is a halogen, bromine in this case. All right, so let's take a peek at this. So when we looked at the reaction to ethene, it was of no consequence. If you add water to ethene, you know, the OH is going to go on one of the carbons, the hydrogen is going to go on the other carbon, and you're going to get that molecule. Well, if you turned it around, you would get this molecule, but because there's only 2 carbons in this compound, those are superimposable. I could take this and flip it around and drop it right on top of B, right? I could take A and drop it right on top of B. Same compound. All right, now, with me? Agreed? You'd vote for that? All right, well, let's take a look at propene. I could take my water, which is an unsymmetrical reactant, and I'm just putting lines from other hydrogens, and you're going to break that bond between the water. You're going to break a bond right here, and you're going to get this product. And if the water molecule presented itself this way to the propene, what would you get? You would get the OH on the end. You see that? And the hydrogen in the middle. So I'm only putting the water molecule. I'm just showing that these are all hydrogens out here. But I'm drawing these just to show you there's our water molecule. What was our water molecule has now added across that double bond. And you can see, I think, I hope, that you can't superimpose those two molecules on each other. Those are two different compounds. In this case, the OH is on the end, and this is where we get the name 1-propanol. That's an O there. Propanol. And here the OH is in the middle, and that's 2-propanol. And you might sit there and say, well, I wonder if you get half of one and half of the other one. Maybe you get both products, 50-50 mixture. Well, about 150 or more years ago, Markovnikov wondered those same things. And he started reacting water with alkenes and finding out, what do you get? What do you get? What do you get? And in this particular case, greater than 85% of the product was 2-propanol. And that's why we refer to that as our major product. You do get both products, but you get a whole lot more of one of them than the other one. You get more of the 2-propanol, and less than 15% was 1-propanol, minor product. On your homework, I have several different places, several different questions where you're hydrating an alkene, and I'm asking you to draw the major product. So if it was this case, the hydration of propene, you would just draw this product, 2-propanol. Okay, well that's good enough. But now, well, even before we ever get to the question of why, Markovnikov didn't know why either, but he started wondering, is there any way I could predict, if you gave me a new alkene, gave me a whole new alkene, and you said, okay, I'm going to hydrate this alkene, what do you think will be the major product? Can I figure that out? So he hydrated lots of different alkenes, and he came up with Markovnikov's rule. And let's take our propene, look at it a little bigger here. Now we know from empirical evidence, that means we actually went in the lab, did it, and analyzed what the products were. So empirically, we got direct observation of what is the major product. And the major product is this one. There's our water. The OH is going to add to the middle carbon. And what did Markovnikov come up with? He said, okay, on the unsymmetrical reactants like water, the hydrogen is going to add to the carbon with the most hydrogen already on it. And the other part of the molecule is going to go on the other carbon. Okay? Hydrogen goes to the carbon of the carbon-carbon double bond that has the most hydrogen. Okay? Hydrogen, hydrogen. Hydrogen goes to the hydrogen. And the other half of the molecule goes to the other carbon. Now notice that over here you got 3 hydrogens, but this isn't in the double bond. So don't get confused over here. Can't add another hydrogen over here. It's saturated. But you can add a hydrogen to that carbon. You could add one here. But this is the carbon that has 2 hydrogens, so the hydrogen goes to that carbon. And then that leaves the hydroxide going to the other carbon. And just so you recognize it, the same exact thing goes for hydrogen halides, just like water. Water and the hydrohalides, you're going to add a hydrogen to one carbon, and you're going to add the other half of the molecule, what's left over, to the other carbon. So same Markovnikov's rule applies, whether it's water or hydrohalogens. The hydrogen goes to the carbon with the most hydrogen, and the bromine would end up right there. So if you added hydrogen bromide to propene, you would get 2 bromo. The major product would be 2 bromo propane. All right? And this is Markovnikov's rule. Markovnikov's rule. You notice that the majority of the hydrogen went to a specific end of the double bond. He formulated an explanation. The hydrogen of the acid. So this is treating water as like a weak acid. Most often goes to the end of the double bond, which had more hydrogens attached initially. So look at your starting alkene. Draw it correctly with the right number of hydrogens on it, and then you can determine what the major product would be. There it is with hydrogen bromide. So this is your major product, 2-bromopropane. And this is the minor product, where the bromine goes on the end where you had the 2 hydrogens to begin with. Markovnikov's rule, important rule for predicting major product. Now, keep in mind, most of you, probably every one of you, have a bottle of isopropyl alcohol at home. And you can see how easy it is to make. It is the major product of the hydration of propene. You're going to get gobs of isopropyl alcohol and only a little bit of 1-propanol. And they probably make that, distill it, and they sell this for, $1 a gallon, and they sell that for $5 a gallon. Okay? Because this is in short supply. It's not as easy to make. And if somebody specifically wants 1-propanol, it's in shorter supply than isopropyl alcohol. Don't worry too much about this. You can hydrate alkynes. You can hydrogenate alkynes. Let me let's just look quickly at the hydrogenation of acetylene. Hydrogen will add across that triple bond. But what do you get? Well, one of these will get you here. One hydrogen. Then another hydrogen will completely saturate. So what this basically says is where an alkene plus 1 hydrogen gets you to an alkane, an alkyne plus 2 hydrogens gets you to an alkane. You see that acetylene is lacking 4 hydrogens. You are not going to saturate it with 1 molecule of hydrogen. You need another one to get it all the way. So just reacting with 1 hydrogen gets you to the alkene. 2 hydrogens gets you to the alkane. I know I'm going to be going a little fast here. Some of the things that I want you to be aware of, I'm going to just cover quickly. And some of the things you really need to understand and apply really well, like Markovnikov's rule, I'll dwell on a little bit more. These I'll leave for you to do. Well, let's just do one. Let's do one. Let's do this one. And what is the major product? What is the major product going to be here for B? Okay, I haven't written out all the hydrogen. I've got it right here. Here's the molecule. I have not written out all these hydrogens. I've just focused on the double bond. But did I translate the kind of hybrid condensed and structural formula correctly to a structural formula here? Okay, this is what I would recommend you do. Work off of a structural formula. And you're going to be reacting water with this. You're going to be reacting water with this. It's an unsymmetrical reagent. Let me number these carbons. 1, 2, 3, 5, 6. So where is the OH going to go? It's going to go on carbon 2 or 3. That's the only choices. Has to go on a carbon that's in the double bond. Can't go anywhere else. Everything else is saturated. This is your point of unsaturation. This is where the addition takes place. Carbon 2 or 3. The OH is going to go on 2. Why? There's more hydrogens on carbon 3. There are no hydrogens here. That's why you go down there and you kind of look at it. There's 1, 2, 3, 4 bonds right there. No hydrogen there. So if you're not drawing your alkenes properly, you're going to draw the wrong conclusion. You need to draw them properly, get the right number of hydrogens on there. 1, 2, 3, 4 bonds, no hydrogen. 1, 2, 3, 4 bonds, there's 1 hydrogen. Markovnikov says the hydrogen goes to the carbon with the most hydrogen. So let's just get that one down there. And so this is going to end up right there. And this is going to end up right there. And that is going to go away. And we're going to get that alcohol. Don't worry about naming it right now. We're not in chapter 12 yet. Okay? So that's how you predict the major product. And you just fly back around here. These are symmetrical, so it's not a big deal. You just put a hydrogen on each carbon. You just put a bromine on each carbon. These are unsymmetrical. You have to apply Markovnikov's rule to B and D. All right, that gets us here. We're still talking about carbon-carbon double bonds here. This is really worth noting because we are surrounded by plastics everywhere we go. We're in the plastic industry. Plastic bags are keeping our sandwiches fresh. Plastic is what our chairs are made out of, and our bumpers on our cars, and our cases for our computers, and on and on and on. Plastic is just everywhere. So this has been, these are polymers, and the majority of them are made by the polymerization of alkenes. That's where you get the majority of plastics. So what does that look like? So all of this stuff, CDs, DVDs, artificial joints and heart valves, all kinds of stuff. Soda bottles, water bottles, all over the place. It's all coming from crude oil, starting from crude oil, and then you distill out of that or make out of the crude oil the alkenes, and then you polymerize them. So what does that look like? Let me just try to, polyethylene. You're all familiar with polyethylene. Ziploc baggies. There is low density polyethylene. That's a Ziploc baggie. High density polyethylene. We'll see what they use for high density polyethylene. So it is polyethylene. And what is ethylene? It's ethene. So the common name for ethene is ethylene. Poly means many. The Polynesian islands are many islands. Many. A polymer is many mers. Does that help you? Does that help you? What is a mer? A monomer. A monomer. So here is our monomer. It's ethylene. Here's another monomer. Here's another monomer. We are going to polymerize that. This produces a lot of heat. And what happens, I'll kind of do this quickly, they add some sort of a catalyst or initiator. They talk about it as an initiator. Those that are making these things, they would start it with a little bit of an initiator. And what that does, so this plus this is going to go to this. This is a free radical. This is a unpaired electron, which are extremely reactive. You get those in your body, your body needs antioxidants to soak these up because they're very, very, very reactive, free radicals. So this thing comes in here, and so what's happening is that, remember, this is 2 electrons here. Looks like a smiley face. Looks like an emoji of some sort. All right, this electron comes in here, and this electron comes in here, and you form this bond. And what's this electron do? It gets propagated over to the front of this carbon, and you got another radical. And so it propagates now. It smashes into another one of these, and you get this. And the free radical gets pushed out to the front of this, and it plows into another one of these, and you get this. Okay, so there's one ethene, there's 2 ethenes. You now have three ethenes, 4 ethenes, and it's just going like this, very, very rapidly. Produces a lot of heat. It goes fast, and you are polymerizing ethene and getting polyethylene. And so you might see it, written like, let's see if we got it on the next slide. You might see this thing written like this. With an N down here, with N is equal to the degree of the polymerization. What do we mean by that? There might be 1,000 ethenes that are making low-density polyethylene, and 2,000 or 10,000 of them making high-density polyethylene. It just they carry it out further, and it keeps getting heavier and heavier and heavier, and thicker and slightly different properties. Natural rubber, 2-methyl-1,3-butadiene. This is what you get out of rubber plants, isoprene. And you can polymerize it into rubber. It's a polymer. See, here's your monomer. Your monomer is isoprene, and rubber on the car tires and other places where there's rubber, this is the repeating unit. This is the monomer that has now been attached 1,000 times to one another and made a polymer. This would be a liquid or a gas at room temperature, and that's a solid rubber. Teflon. Instead of starting with ethene, they start with tetrafluoroethene. I was just on a discussion last night referring to one aspect of this, a byproduct of this reaction. But in ethene, these are all hydrogens. But in tetrafluoroethene, those are all fluorines. You polymerize it into, this is the copyrighted name of it from, I don't know if it's 3M, Teflon. It's called Teflon. That's your non-stick surface. Instead of being polyethylene, it's polytetrafluoroethylene. It's also in Gore-Tex. All right, now this is a handy little chart for you to be aware of. These are, if someone has their water bottle tightly capped, turn it over and you can see a triangle. So if you have a water bottle, one you bought, like the one back there, who is that in the corner back there? Yeah, so you bought one. If you turn that upside down, if it won't spill all over your computer, can you see a triangle on the back, on the bottom? Look for a triangle. No, on the bottom of you. Look at the bottom. There, right there. There you go. Yeah, do you see a triangle like this? It might be on the side, but these triangles are telling you what that plastic is. One is polyethylene terephthalate, which is what your water bottles are. Those are PETE plastic, polyethylene terephthalate. Now here is low-density polyethylene. So that's the one we were just talking about. Bread bags, sandwich bags, high-density polyethylene, milk and water jugs, juice and bleach bottles, high-density polyethylene. That's the simplest ones. Polyvinyl chloride is, if you've seen plastic pipes in your house, those typically are made out of polyvinyl chloride. They're not being made out of polyethylene. Those hot water going through those will get real droopy. Those will start being like spaghetti. But the polyvinyl chloride will keep its integrity and strength. So different plastics. Polystyrene, these are, so a number 6, this is your coffee cups, your disposable coffee cups, polystyrene. And then, like I said, that's your water bottles. Number 7, this is the one, if you see a number 7, if you've got plastics at home that you don't want to put this stuff in the microwave. This is can be all kinds of different plastics, some of which might give off bisphenol A, BPA. You see the BPA label on a lot of, like your water bottle, if you bought that, it'll say no BPA. Probably says no BPA on that. So it's one of these, maybe this, I'm not sure what plastic it would be, but it's not a plastic that will leach out bisphenol A, which you do not want. You don't want bisphenol A leaching out into your foods and things like that. I was hoping to get into chapter 12, but I'm not sure I'm going to be able to do that. We still have to cover aromatics. What slide am I on? Okay, we got to do aromatics here. All right, so what I want to tell you is aromatics are not alkenes. They're not alkynes. They do have double bonds in them, but the double bonds are conjugated. What do I mean by that? Alternating double bonds. Double, single, double, single, double, single in a ring structure. That's an aromatic compound. This is the most common example of an aromatic compound, benzene. Benzene. Let's take a look at its structure. I'm not going to do a deep dive into the, some of these slides will have the molecular orbitals that are involved. That's not necessary in this course, I don't think. I mean, it's very interesting. It's very relevant, but here's what they're talking about. You could draw, you can see that I could draw a double, a single, double, single, double, single here, or I could start single, double, single, double, single, double. I could draw two different structures for this same molecule, benzene, and we call those resonance structures. Those are identical and probably not what real benzene is, the sum total or the average of those two right there. It's a little bit more like this. If I were to average that, what would I have? I would have, in other words, I'm going to take a double bond here. I'm going to take one of my double bonds, and instead of saying it's between these two carbons and there's a single bond there, I'm going to say, no, it's a little bit more like there's a half a bond there and half a bond there. Then I get around to my other double bond, and there's a half a bond there and a half a bond there. And I get around to my other double bond, and there's half a bond there and half a bond there. So you know what we actually do? We draw a circle. We just draw a circle in there instead of three distinct double bonds. And that's benzene. Here's looking at the molecular formulas. So there's kind of a pi cloud, or a cloud, a molecular orbital where a bunch of electrons can be in there, that the electrons are being shared between these 6 carbons, and then the other half of them down here below the ring, and you get a pi cloud above and below the ring. It's flat. It's flat. It has a little bit more stability. And so these are all acceptable drawings of benzene, showing the 3 distinct double bonds. Here would be a line diagram showing the 3 distinct double bonds, or just drawing it as a circle. There's it a little bit more structurally. That's structural. There's only one carbon, or one hydrogen on each of these carbons. Those are all benzene, okay? This is carcinogenic, benzene is. Benzene is a carcinogen, so it's not really something to play with. So let's take one of these drawings, like this one. And let's just compare it with, so here is, I always kind of draw my 6-membered rings like that, so I can put a double bond there, double bond there, double bond there. That is not this, that's cyclohexane. It is not this. This is, what is that? What's the name of that? Cyclohexene. That's cyclohexane, cyclohexene, and now we have, this is not cyclohexene, this is benzene. This is its common and IUPAC name. So it only has an IUPAC names. It only has one name. Benzene. Okay, naming other benzene compounds. This is chlorobenzene. Chlorobenzene. Nitrobenzene. It's a nitro group on there. Ethylbenzene. It's an ethyl group. It's not an ethene. It's an ethylbenzene. Here is one you should have a 3x5 card of for chapter 11. Benzene, I would put benzene on a 3x5 card. And this is toluene. So this is benzene with one methyl group on it. These will eventually become 3x5 cards, but I wouldn't worry about them right now. We're going to see this one in chapter 12, this one in chapter 14, and this one in chapter 15. So don't worry about them for right now. We'll get to this one pretty soon, like I said, chapter 12. But this one I would definitely get a 3x5 card for toluene. All right, now we skipped over something here. A traditional way of naming groups on a benzene ring that we need to understand. So let's take toluene. Let's go off of toluene. All right, so let's go over here. We'll go to this molecule here. There's our benzene. There's a methyl group. We could put a methyl group right here, a second one. So this orthometa-para nomenclature comes into play when a benzene ring has two things on the ring. All right? So here we would count one of these as carbon number 1, and then we would go over to the next one. We would go over to the next one as quickly as possible. So I would move this direction over to that one, 1, 2. So this is like 1,2-dimethyl benzene, or it's 2-methyl toluene. This is 1, 2, 3. This is 1, 2, 3, 4. And those are the only 3 possibilities. I mean, let me just convince you, if I were to move over one more carbon right here, and you'd say, well, isn't that 1, 2, 3, 4, 5? Well, look at this. 1, 2, 3. I'm going to count over to get there the quickest, so it's 1, 2, 3. It's the same as this one, 1, 2, 3. And hopefully on a Monday, it isn't too early to have you in your mind imagining this flipping over on top of that, right? This would be superimposable on that. So this is not another molecule. It's just that one twisted around in another direction. Same thing. So we can ignore this one. This is not another molecule. Those are the three possibilities. And this actually, when you get two methyl groups on here, this is called xylene. But I want to just use it to illustrate this ortho-meta-para. Instead of calling this 1,2-xylene, it has come up with the term ortho. It's ortho-xylene, or you would just see it. You might be reading a paper, and it refers to O-xylene. And this one would be meta xylene, or just simply M-xylene. And this one would be called para-xylene, or P-xylene. All right? So what we have here is we've got an ortho, a meta, and a para position. And this is not IUPAC. This is grandfathered back, or a traditional way of doing it. Let me give you a little way of remembering it. So on the benzene ring, we've got something here, let's say a methyl, and we have the ortho, the meta, and the para positions. So para would be something on this ring that's on the opposite side of the ring or halfway around the ring as the methyl group. So here's how you remember it. This is a boot, and just think of stomp. All right, so your memory trick here is to think of the word stomp. So the ortho, meta, and para come in the OMP order. This is your carbon 2, 3, and 4 positions. So, well, let's just try to apply it. Try to draw that structure. Para-dichlorobenzene. Para-dichlorobenzene. So there's benzene. Where do the two chloro groups go? One at the top and one at the bottom. So we have para-dichlorobenzene. In other words, we don't have a 1 or a 2 in this name. I mean, alternatively, I might have had 1,4-dichlorobenzene. This would be the IUPAC name of it. That would be the IUPAC name of it. There's 1, 2, 3, 4. But this is the para position. Carbon number 4 would be the para position to that first chloro group, and it would just be para-dichlorobenzene. And you know, oh, it's in the para position, opposite it. It's in the meta position. It's in the ortho position. So you need to understand what ortho, meta, and para positions are on a benzene ring. They only apply when there are two things on the ring. In other words, just benzene itself, any one of the carbons is carbon number 1. They're all identical. Okay, we have a few minutes to cover just two other points. Here's an example. Let me draw this out. Here's our double bond, our CH2. We've got a CH and a CH3. And on here, we've got a benzene ring. What are we going to call that? Well, this is your next substituent. When a benzene ring is hanging on the side of a carbon chain, it is a phenyl. P-H-E-N-Y-L. Phenyl substituent. So we got methyl, ethyl, propyl, butyl, phenyl. Phenyl. You can see the YL. It's kind of pointing to the fact that we're talking about a substituent. There's a hydrogen here, 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 and here, but this hydrogen is gone. It's now, this carbon on the benzene is attached to that carbon on the chain. That's a phenyl substituent. We'll talk about this in chapter 12, so don't worry about that right now. These are our heterocyclic aromatics. Benzene is not the only aromatic. There are pyrimidine rings, heterocyclic, carbon and nitrogen in the same ring. Purine rings. These are very much prevalent in DNA and RNA structures. These are your nucleic acid bases. Pyrimidine, purine. Here's pyrrole. I think I have you drawing some of these in the thing. Okay, and one reaction, and this will finish chapter 11. Halogenation of benzene, or toluene, whatever, but of an aromatic. All right? Even though there are double bonds in here, or you could draw them, you are not going to add chlorine across a double bond. This is not like halogenating a alkene. This is an aromatic, and it is substitution. Only one chlorine comes on the benzene ring, and you get HCl. And you have ferric chloride as your catalyst. So this is a reaction. In chapter 11, so study that reaction. In chapter 11, you should know very, very clearly 4 addition reactions to alkenes. You should understand basically polymerization of alkenes, and you should know the halogenation of benzene. All right, those are your reactions that I would hold you accountable for in chapter 11. You should understand how these proceed. Now look at this, is kind of going a little bit more like halogenating to an alkane. It's substitution. One chlorine goes here, the hydrogen comes off. You only get one chlorine on the product. Okay, chapter 11 homework is due on Wednesday, and we will really go after chapter 12 very, very hard on Wednesday. So I would recommend you be a little bit familiar with chapter 12 coming in here. Primary, secondary, tertiary alcohols. I'm going to explain what those are, but you might want to be familiar with what is a primary, a secondary, a tertiary alcohol. How do alcohols oxidize? All right, I'll see you Wednesday.